In this video, I want to talk about the composition of functions. And the composition of functions is the most natural way of combining two functions. Let's suppose we have a function f going from a to b, and then a function g going from a set b to c. We're going to let x belong to a, and y belong to b, where f of x is equal to y. So we pick an element in a, input that into my function f, and we get the output y. We'll then let z be an element in c, where g of y is equal to z. So I input an element x into my function f, I get my output y, I then use that as my input for g. We denote this as g of f of x or g of f of x. So both of these are valid ways to denote this idea. Here's a small diagram demonstrating the idea of the composition. I have an element x in a. I apply my function f to get an element y in b, and I then apply my function g to get an element z in c. The first thing I want to show about the composition, if f and g are injective, then g of f is injective. If both my functions are injective, then the composition is also injective. Let's suppose g of f of x1 is equal to g of f of x2. In order to show this is injective, we need to show that x1 is equal to x2. Since g is injective, we know that f of x1 is equal to f of x2. That's the definition of g being injective. And since f is injective, we know that if f of x1 is equal to f of x2, then x1 is equal to x2. So I started with g of f of x1 equal to g of f of x2. I showed x1 has to be equal to x2. Therefore, g of f is also injective. The next piece, if f and g are surjective, then g of f is surjective. If both my functions are surjective, then the composition is. Let's let z belong to my set C. In order to show that g of f is surjective, I need to show that there's an element x in A that maps onto z. Since we know that g is surjective, there must be an element y in B such that g of y is equal to z. And since f is surjective, there's an element x in A such that f of x is equal to y. So both of those are just the definition of f and g being surjective. So now we have that g of y, which is the same thing as f of x, is equal to z. So I started with an element in C and showed that I had to find an element in A that maps onto it. So therefore, this is surjective. Let's do some examples with actually finding the composition. Here I have a function f going from r to r defined by f of x equal to sine x, and g goes from r to r defined by g of x equal to e to the x. I want to find g of f of x. Well, this means g of f of x. I know what f of x is, so I'm going to replace this term here with the definition of f of x. And then g of sine x means take my function g, and everywhere you see an x, change it to a sine x. So g of f of x would be equal to e to the sine x. Let's find the opposite as well, f of g of x. Well, this time I have the definition for g of x, so I'm going to replace that. So now I have f of e to the x. And this means take my function f, and everywhere I see an x, change it to an e to the x. So f of g of x is sine e to the x. Here I have one, f goes from a cross b to b cross a, defined by f of xy equal to yx. So I take an ordered pair and just switch the coordinates. G goes from b cross a to b, defined by g of yx equal to y, so it takes the first coordinate from the ordered pair. So this time I want to find g of f of x comma y. This means g of f of xy. I always start with the inside. I know the definition of f of xy is g of yx. And then I know g of yx means y. So g of f of xy is just y. Combining these two functions outputs the second coordinate. For this one, I'm going to let A be the set of elements a, b, c, d. And f and g are both functions going from a to a, defined here in this tabular form. Just as a reminder, this means that f of a is a, f of b is c, f of c is a, and f of d is c. So the first row is the inputs and the second row is the corresponding outputs. I want to find both f of g and g of f in this same tabular form. Well, we know we're going to have a, b, c, d, and we need to figure out what their outputs are. When we're working with composition, we always work inside out. So for f of g, we need to start with g. G maps a onto b. We then use b as our input, and we get the output of c. For b, g maps b to a. Using a as our input, we output a. G maps c to b, and using b as the input, we output c. Finally, g of d is a, and using a as our input outputs a. So there's f of g. Now let's do g of f. Since we always work from the inside out, we're going to start with f and then g. So f of a is a. Using a as our input, we output b. F of b is c, and using c as our input, we output b. F of c is a. Using a as the output, outputs b. And finally, f of d is c, and using c as our input, outputs b. So there would be my two compositions.